Okay, so as promised, our next session of review is going to be on free body diagrams. Ooh, let's see if I can do better on that. There we go. Free body diagrams. And we've done a lot of these, so I know you guys know how to do them, but just as a refresher, the things to keep in mind. Number one is point the arrow in the direction of the force. Make sure that the length indicates the size. So be careful that if you have two forces that are different sizes, you make them clearly different sizes. Okay? Make sure you do those things because that's a simple way to earn points. Now, the third thing is what forces can I use? So our family of forces is force tension, and that's rope, string, cable, any of those things. Force normal is from the surface of contact and it is always drawn perpendicular to the surface. Also, the force normal, something to keep in mind, is it comes from the surface so if you are asked to draw from where they come, this one needs to be drawn on the surface of contact. Okay, another one that is like that is force of friction. So these two don't act at center of mass. All the other ones we work with basically do. So all of the rest of them act at the center of mass unless they are drawn when we're doing torque so that they're clearly shown that they produce a torque. So force of friction is always parallel to the surface of contact. And it is going to be, it opposes the motion, or it opposes change in motion. And I think that's where we need to be careful. It's opposing the change in motion. So it sort of emanates from the idea of inertia. So if an object is at rest, the frictional force is going to try to keep it at rest. If the object is in motion, the force of friction typically goes in the opposite direction of the motion, but it can go in the direction of the force occasionally, or the motion of the object, depending on what you're trying to have happen. So we'll give you some examples of each of those in just a minute. But those two are a little bit different than the other guys, so you might want to keep that in mind. So we also have force gravity, also called weight. It always comes from the center of motion, and it is mass times gravity, which is m times 10, or m times 9.8. Pick one and be consistent. It doesn't matter if you use 10 or if you use 9.8, but it does matter that you're consistent. So there's force of gravity. Then we also have force electric, which we don't do in this class, but we do in physics 2. We have force magnetic, which we do not do in this class, but we do in physics 2. And then we have, we have elastic or spring force. Spring or elastic forces, where the object returns to its normal size and shape, or it compresses and then expands back to its normal shape. So force spring or elastic forces. Force due to a spring has a formula. Force due to a spring is negative kx, where k is the spring constant, and that number will be the same for any particular spring. It'll change values when you go from one spring to another, but for a particular spring, that number is a fixed value, and then in this case, x is the displacement. X is the displacement. So tension, force normal, force friction, gravity, and weight, a lot of those formulas, you don't have formulas for the forces, and so you have to use the free body diagram to figure out what the force is. In some cases, we do have a formula for it, and we will look at that in just a minute. So, and then of course, if we don't know what the source is, force applied is sort of a catch-all term. It's a generic force. We don't know the source usually. And that's usually what we use there. Or we're treating, for example, a car that has, a car is really a system of a lot of different parts in motion and things. But we will call force applied maybe from the engine, because we're treating the car as if one object, not a system of objects, but one object. So we would call the force from the engine the force applied. So a catch-all term for if we don't know the source, or it's just they tell us in the problem a force is applied on and we don't know why. So those are our catch-alls. Now, thing to note here real quick, before I go to the next page, well actually let's go ahead and go to the next page, is that force centripetal is a special case. Force centripetal is mv squared over r. Acceleration centripetal is v squared over r, and these are not standard forces. We don't put force centripetal on a free body diagram. We put the source of the force. So, if you're talking about a ball rotating around with a string, okay, so the ball rotating around the string provides tension. The tension allows the ball to go around in a circle. So the centripetal force is due to tension, so the free body diagram is going to have tension on it. Second thing, one of those things that I see crop up a lot, and I know I did a mistake and I fixed it on a video, but one of the things you need to remember is that if you have an object on a table and we are pulling it with some amount of force, like 200 newtons here, one of the things you need to remember is the free body diagram is going to have a force, tension, it's going to have a force normal, it's going to have a force due to gravity, and it may even have force friction. So it might look something like this. But one of the things I want you to remember is that force normal does not always equal force gravity. For example, in this situation, there are two upward forces. One is the y component of tension, and the other is the force normal. So in this case, you have two ups and one down. So make sure you, number one, draw the picture correctly, and then number two, use your picture correctly. So make sure that you pay attention to those kinds of things. So, best way probably to do this is just to work some problems. So what I'm going to do, as I always do on these review videos, is I'm going to work problem number 78 that you see across from me. And if you would like to pause right there, you're welcome to do that. So, number 78, an unusual picture. So, what I'm going to do, I know it's a multiple choice question, and I know I could probably reason it without doing any math, but I'm not going to do that. I'm going to draw my free body diagram. So the first thing I have is I know there's a force due to gravity pulling down on the block. That's the first piece. The second piece is that there is a force over here of 100 newtons. And of course, on a real free body diagram, you would not do that. You wouldn't put the numbers, you just put force applied. Because that's what they tell us. A block is being pushed up against a wall. It's kind of a weird way to push a block up against the wall, but maybe you're holding it up there so that you're going to hammer something in or keep something level or draw a line, things like that. They tell us this coefficient of kinetic friction is 0.30 and the coefficient of static friction is 0.50. What is true of the friction acting on the block after 1 second? Well, what we need to consider here is which way would friction act in this case? Since there's a force going up the plane and there's gravity down, we have to ask ourselves, does the block move up? Which way does the block move? What did I just do? Block moves. Which way? So give me a second to ponder that. If this was a frictionless wall, we know the block would move up. And so friction would be down the wall. But in this case, it's kind of like, what's going to happen here? So what we've got to figure out is, does the block move? Does it even move? So let's work on that. What forces do I have? So let's assume block stays stationary. This is how I'm going to start. If it's not stationary, then it answers the question for me. So what forces do we have? Well, we also have, and we didn't put this one on here to start with, but there is a force normal that pushes to the left from the contact surface of the wall and the block. So we have to remember that one too. So here we go. If I'm doing this, since it's multiple choice, I don't actually have to, move stuff around too much. So I'm going to go ahead and put on my picture, this is the force applied X part. This is the force applied Y part. I know these two are going to be balanced because it doesn't say anything about the block going into the wall or the block pushing back and coming off the wall where it wouldn't be in contact. So those must be balanced. So that means that force applied Y must be equal to the force due to gravity. That's going to be my assumption here to start with. So they tell me the force applied Y. Well, how are we going to find that? So let's go over here. Just don't worry about taking your time. Take your time, but be quick, but don't hurry, because hurrying tends to cause silly mistakes. So the angle that we're working with here on the triangle, we see that in the picture we're told that this angle is 60, so this angle must also be 60. So this would be the Y component over here. Y over 100 will equal the sine of 60 degrees. So Y equals 100 sine 60. So I get this down here and I go, okay, I can do that. 100 times 60 sine. 100 times the sine of 60 is 86.6. So 86.6 newtons. And my force due to gravity is 6 times 10. So 60 is less than, whoops, that cleaned up. 60 is less than 86.6. So block moves up, and we must have kinetic friction. And if the block is moving upward, the kinetic friction would point, force friction kinetic would be downward. Okay, so there's the way to apply the free body diagram. Now, can you answer this question without doing all that math? Yeah, probably, because you can see that there's a force of 100 up. Now, granted, 100 up is not all directly straight up, but the mass of the block is only 60, So it stands to reason that we would have the ability to, we'd have the ability to push the block upward so that it begins to move. It's, your guess would probably be that it's moving just because of the size of the forces, and in fact, in this scenario, that would be the correct thing to assume. But there's the math in case you saw this on a free response. Okay, let's do one more like that. So do number 75 or 79, and then we're going to go on to some free response questions. So I'll give you just a second to pause it if you want to right here. I'm going to take a breath, and then I'm going to start working. Number 79. Number 79. Alright, so homeowner pushes a lawnmower across a horizontal patch of grass with a constant speed by applying force P. The arrows indicate the directions, but not necessarily the magnitude. So, arrows do not show size. Okay? That's what they tell me. Which of the following relations among the various forces is correct? Okay, so the man has, so we have forces on the thing. Here's our force P, and then we have a force friction. AP uses small f for friction. So they're going to use little f everywhere they're going to have friction in a problem. We have a normal force up, and we have the weight down. So they tell us that he's going to go at constant speed. So we do know we have constant speed, and what that tells us, the sum of the forces must add up to 0. So what does that tell me in this picture? Well, first of all, let's look at our up and down forces. We have weight down, we have normal up, and we have part of force P. Part of P is also going to do. So P, the Y value is going to be down as well. So that one is going to be down as well. Just a moment. Okay, so when we're talking about this problem, we know from our free body diagram that what this does to us is that the force normal up has to be equal to weight plus the Y component of the P force. So force normal is bigger than weight, and force normal is also bigger than P sub Y. Okay? In addition to that, if we look at the horizontal forces, we have a horizontal force FPX, we're going to call it FPX, and it goes to the left, and force friction goes to the right, and those two are going to have to be equal to each other because, once again, we are at constant speed. So what we have here, when they ask us the question about which is correct, we know that part, so we look at this, they're comparing P and F. So what's going to be true of the F sub P compared to the force of friction? Well, force of friction is equal to the X leg only. So the force of friction being equal to the X leg means the P force has to be bigger than the F force. So that gets us down to A or C. Then they ask us about normal and weight. And normal and weight, as we showed right here, normal has to balance weight and the force that the man is pushing down with. So normal has to be bigger than weight. So our correct answer is actually letter A. So that's how we're going to analyze that one. Okay. Now, we're going to go down and do a free response. And yes, there are hundreds of these problems. I have lots of problems on this. So let's look at, let's get past circular motion. we're going to do this right here, number 203. We'll do number 203, and I'll give you a minute if you want to pause. I'm going to put in a new page again so that I have a nice clean sheet to work with. Maybe I have two. Oh, no, just one. And I'm going to work the 2003 B3. So, for those of you that are paused, I will catch you on the back side of the pausing. On the dots below, we're supposed to represent the forces on each person. So on student A, my dot for student A, I will have a force tension. Force tension that's going to try to pull that person up. So B is holding on, so student A's arms are going to get pulled up in the air. So they're going to have to apply a force down on the rope to hold the other person up. So student A's getting pulled up. There's also a force normal, and to draw it like AP wants to draw it, we got also a force normal up from the floor, and then we have the force gravity down. That's the weight of student A. Student A's weight. And yes, I hate the way that looks. That makes me crazy. So, force normal. Now, for student B, what do we have for student B? Well, student B is not in contact with the floor, so there's no normal force. But student B does still have a weight, force due to gravity for B. And this time they're getting pulled up by tension from the other kid. And we don't know what's happening, except they tell us that right now we are at rest. So we're at rest, which means all these forces should add up to 0. Okay? So let's just make it easy for ourselves. I'm going to fill in, I know that force gravity for A is 70 times 10, so this is 700 newtons. And force gravity for kid B is 60 times 10, so that's 600 newtons. So that's going to help me get started. And so what have we got really? It says, Part B, calculate the magnitude of the force exerted by the floor on student A. Well, I'm going to have to match this with its action-reaction pair. So I need to figure out that force tension. So the first thing I'm going to do in Part B is this. I'm going to go, okay, sum of the forces for student B is going to be M times 0. We're at rest, right? So force tension minus force gravity for B needs to equal 0. So force tension must be 600 newtons. Now I'm actually ready to answer the question they asked me for. Okay? So let's do the question they asked me for. So for student A, sum of the forces on A also equals 0. And the forces on A are normal up, tension up, and gravity down. Whoops. Let's write as gravity down first, and then we will. Do not forget to write these statements. Why should you not forget to write these statements? Number one, because you earn points for it. AP will want to see this every time you work a problem with free body. So do not forget to do these statements. That's the simplest and easiest way to pick up points. And we want to be point grabbers. Pick up every single little tidbit of stuff we can get to help ourselves. So now we're going to fill in what we know. I don't know force normal. I know force tension is 600 and it's up in this part. And force gravity is 700, so it's down. And force normal will then be 600 minus 700 would be 100 newtons. So there's my answer to part B. Okay. So far, so good. Now, student B is now going to climb the rope with an acceleration of 0.25 meters per second squared. Okay, kid, why'd you go and do that? Well, let's put this in here. So, part C. If student B now accelerates, so that tells me the sum of the forces for student B is equal to mass times acceleration. Okay? And the kid's going to accelerate up the rope. So what does that mean in terms of what we do here? How is he going to ascend the rope? Well, we're just going to take it at face value, and we're going to take the fact that the kid is 60 kilograms, and he's going up at 0.25 meters per second. And we're going to use the same forces we had before. Force tension minus force gravity must equal this value. They're asking me to find the tension in the rope now. Well, so force tension minus 600 would equal, let's see, 1/4 of 60 is 15. So force tension is now 615 newtons. So now the student A now feels like the rope or the kid on the other side is getting heavier. What's really happening is the kid on the right, student B, is pulling down on the rope. But as he pulls down on the rope responds with the action-reaction and pushes the kid, the normal force pushes the kid up the rope, or friction pushes the kid up the rope. Either way is fine to think about for right now. And so now the kid on the left has to support more force because of the acceleration of student B. Now, it says, as student B is accelerating, is student A pulled upward off the floor? Justify your answer. Okay, so how much more force did student B put into this problem? It's like the 700 kid now has to support a 615 Newton child. So, is that enough to make them leave the floor? Well, let's go back and look at that for just a second. We're going to be looking at particularly this part. So, does student A get pulled off the floor? Well, what would have to happen for student A to get pulled off the floor? Let's write what we had to start with. So, force normal, if we're pulled off the floor, we no longer have this force, because you're not in contact with the floor, because you got pulled off the floor. And that would mean that now we'd have force tension would have to equal force gravity, or if they're unequal, tension would have to be bigger than gravity. So our question is, which one do we actually have here? Well, the student weighs 700, but the force tension is only 615, so no, student A is still on the floor. So student A is still on the floor because the tension would need to be greater than 700 newtons to pull them off the floor. So what's really happened here? What's really happened is the normal force is now supporting less weight. So the tension in the rope pulls the kid up a little bit more, holds more of that student A's weight, and so force normal from the floor actually goes down a little bit. In other words, if we had a scale, if we were to put a scale reading under student A, then we would have the student A would look like he now weighs less. He doesn't, or she doesn't, but it would appear to us that they weigh less because the normal force has gone down. Okay, that's C and D. Now we've got D, so here's our part D. And last but not least, with what minimum acceleration must student B climb the rope with to lift student A off the floor? Well, now this comes back to a nice easy. Now I want force tension to be slightly bigger than force gravity. Okay? So force tension is going to come from mass of student B times acceleration of student B, and the force gravity is going to be 700 newtons. We're trying to pull, which is the force gravity of student A. So, what do we get? 60 times A equals 700. So A would need to equal, let me pull out my calculator, 700 divided by 60. So a student would have to climb up the rope with 11.7 meters per second squared to be able to lift student B off the floor. Seems a little high, doesn't it? Let's go back and check something. If student B pulls hard enough to get student A off the floor, one of you might be thinking, well, I just need 10 more kilograms. But 10 more kilograms at 10 meters per second is roughly 100 more newtons. So that the A would be correct. A is going to have to be 700. You got to pull down. Hang on just a second. Back that train of thought up. I was looking at the wrong free body. Let's come back here. My fault. I was too busy thinking about what I was going to say next until I need to finish the problem. What forces are on student B? He's going to have a force applied that pulls the rope down, and he has force due to gravity down. And force tension is going to be made up of those. So force tension for the boy on the right, or the girl on the right, is going to be mass times acceleration plus 600. Because gravity is going to pull him down as well. So he's got gravity helping him, and now he just needs to pull up hard enough to get past that student. So the force tension is going to be 60 times A plus 600, and that needs to be greater than 700. So that's where I forgot to put gravity in. So acceleration is actually going to be 100 divided by 6, which is a much more reasonable... Whoops. 1.7. There we go. And that would certainly be doable. 11 meters per second is faster than an airplane actually accelerates, so that seemed a little off when I did that. And so I caught myself, and how did I catch myself? Well, 11.7 is really fast. And with just 25, we were already up to 15, so it shouldn't be really, really fast. If we doubled this, here's another way to check your answer. If I go 0.5, I should be at 630. If I go 0.75, I should be at 645, and you could just do it like that, and that'll put you 1.5, between 1.5 and 1.75, and then you would be able to get the answer from there. So that's another quick estimator way to answer your problem. Okay. Let's see. Let's do one. I think we've done that. We'll do some with springs when we get to springs. And other than that, that's your Free Bodies review, and I hope you have a wonderful day and that this helps you in some way.